physics kids, Mrs. Campbell here. In our last video on thermodynamics, we're going to talk about what the second law of thermodynamics is and what is entropy. So the second law of thermodynamics is really about which way processes occur. All processes always occur in one direction. For example, if you think about things falling, right? Things always fall down. So like water in a waterfall always flows down. Gases will always expand from high pressure to low pressure. In fact, you can kind of think of this like people, right? When you're at one of those pep assemblies and you're squished on the bleachers with all these people around you, you just want to get out, right? And so you spread out. And gases do the same thing. They don't want to be under high pressure. And so if they have the opportunity to expand and move to lower pressures, they'll do that. In our second video of thermodynamics, we talked about how heat spontaneously flows from high to low temperature. And we looked at some simulations where we saw that, remember, high temperature means greater kinetic energy, so moving faster, right? And so they have a greater probability of moving out quicker, and they hit slower moving molecules which have a lower temperature, and they transfer some of their energy until everything reaches the same temperature, which we called thermal equilibrium. So this is really what the second law of thermodynamics is all about, is the direction that processes go to. And so we can think of these in terms of reversible and irreversible processes. And one way to think about it is if we could watch a movie forward and then watch it in reverse, does it make sense both ways? Now, on a microscopic level, we'll see that a lot of processes are reversible. Like when there are collisions between molecules on a microscopic level, whether I play the movie forward or backwards, right, it still seems like, sure, that happened. But if we think about a macroscopic collision, like running a car into a wall, right, we see the forward process, that makes sense. The car is fine, and then whoosh. But the backward movie wouldn't make sense. How does a smushed car suddenly become unsmushed, right? It requires some energy, some effort, some work to get all those crumples out of the car. So that's a process that's macroscopic, and that's irreversible. So equilibrium is actually the state that everything proceeds to because it's the most probable state. So systems reach thermal equilibrium, where their temperatures are the same, because that is the most probable state to be in. So these reversible microscopic events, these collisions between particles, which we could watch forward or backward and wouldn't make a difference, will lead to some irreversible macroscopic behavior, because on a larger level, these macroscopic states, these equilibrium states, are vastly more probable than others. Now you're probably like, what are you talking about, Mrs. Campbell? This is so confusing. Well, I have a great example of this using ping pong balls. So let's watch it. All right, so let's take a look at reversible and irreversible processes and how that relates to equilibrium. Really, what equilibrium is the probability that a certain state will occur. And so I thought I'd demonstrate that by using numbered ping pong balls. Lucky number 7. So what I did is I put all the ping pong balls in one little bucket here. And what I'm going to do is use a random number generator. And every time a number comes up, it's going to switch between buckets. Clearly, this is not a probable state, right? The likelihood that they're all going to be in one container. So what do you think it's going to look like after we do this for a long time? Do you think they're all going to be in this container? Are they going to all still be in this container? Or is it going to be an even mix? Well, let's find out. First number up, number 16. All right, number 16. Number 9. Oh, 20's going back. Where'd you go, 20? right, have we had enough fun for one day? Let's take a look at what we got. We have about an even amount of balls in each one, and we could keep doing this. Is it possible for all the balls to end up in one container? Heck yeah. Is it probable? No. Just like if I throw these balls up in the air, are they all going to come down in one ordered bunch on my table? Well, let's find out. Ready? Hey kids, I need you to come down and pick up some ping pong balls. So we just saw with ping pong balls this whole thing of order and disorder, and it's really what entropy is. Entropy actually is a quantification of the most probable state of a system. Entropy will only increase in a system. So if we take a look here at some particles, right, if we set these particles up in these nice orderly rows and we move one particle, right, that's really obvious. But the more these particles become disordered, right, the more probable that state is. So if I move one particle, you wouldn't really even notice, right? Whereas if I move a particle here, you do. So in entropy is the probability that a state's going to occur, and with two systems that have completely different temperatures, right, as soon as we put them in thermal contact with each other, they're going to mix, and that mixing is going to cause thermal equilibrium. So the second law of thermodynamics says the entropy of an isolated system never decreases, that either the entropy increases until a system reaches equilibrium, or if it's in equilibrium already, it's going to stay that way. So what that means is isolated systems always get more disorder or more random, because that's more probable, right? If you think about your room, right, it is the law of nature then that explains why your room becomes messy, right? It never just suddenly becomes clean. You have to actually clean it. So you can tell your mom that it's really the second law of thermodynamics in action. Of course, that doesn't work in my house. So we know that energy can't be destroyed or created, right? We can convert it to other forms, and usually what happens is we get this conversion into thermal energy. The problem is, and you remember those arrows that were one way on that energy diagram that we saw in our first video, it's because when we've generated thermal energy, this change is irreversible because we get this spreading out, this increase in entropy. Now, can we use thermal energy to create other types of energy? Sure, we can. The problem is that conversion can't be 100% efficient. In fact, we use thermal energy every day to make other types of energy. These are called heat engines. So we know that thermal energy spontaneously goes from hot to cold. So we can use this process of generating this temperature gradient, so we get this heat flow between a hot and a cold reservoir, and if we harness some of that transfer, we can actually create some work. So what a heat engine does is it takes this energy that's being transferred as heat from a hot to cold reservoir, because that's the spontaneous process going from hot to cold, and turns some of it into useful work. Now, the problem is that's never 100% efficient. So how much work can we get? Well, the way we'd calculate that is we'd take the energy that we put in, right? That's what's coming out of the hot reservoir, and how much gets expended into the cold reservoir, how much energy comes out. The difference between that, right, is how much work that we've generated. And we could calculate the efficiency of this engine by taking how much work that the system did, or that we got out of the system, and dividing by how much energy we put in, right, which is the heat that was flowing in. So we can find out how efficient a system is. Now the problem is it can never be 100% efficient, because we can never get this transfer of heat to go right to work, right? It has to flow from hot to cold. So I have to have some of this flow. So because I have to have some of the heat flowing to this colder reservoir, I can't get all of that to become work. Now, like I said, we get a lot of energy actually through this transfer of thermal energy, because a lot of the electricity that is generated that we use to power our homes comes from heat engines. So, right, we burn fossil fuels, right, which produce high temperature steam, so we get this flow of the hot steam to a cold reservoir, and in the process it turns a turbine, and that turbine then, using magnets and stuff we'll talk about in second semester, will generate electricity. The problem is the typical efficiency of a steam power plant is only 40%. So think about how much of that fossil fuel energy that we're actually losing. Now, there is a way to reverse the process, right? Spontaneous processes proceed towards an equilibrium because that's the most probable state, but we can reverse the process, right? I can take the dents out of that bumper in that smashed up car, but I got to do some work. I got to put some energy in to do that. And from a thermal standpoint, we call those heat pumps. So if you have a refrigerator, if your house is air conditioned, you have a heat pump. And what it's doing is it's taking the energy, the heat energy, out of the cold reservoir and pushing it backwards. It's pushing it into the hot reservoir. In fact, if you've ever stood outside of one of those unit air conditioners that are in the windows, if you ever stood outside of one of those, you can feel that hot air coming out because there's a pump in there that's doing work to push the heat in the direction that's not the spontaneous process. So you can go against nature. It just requires work. And that's what I tell my kids when they don't want to clean their room. All right, we're done with thermodynamics. See you guys in class.